All right, so welcome to the CleanStart Meetup in partnership with, we're going to find your seats there, in partnership with Sac State, the College of Engineering and the College of Natural Sciences and Mathematics. Now I'm going to kind of go through these slides really quickly. Our meetups are sponsored by Blue Tech Valley, the Regional Innovation Cluster, and Sac State, all through a big CEC grant that's helping drive innovation in clean tech in the Sacramento region. Our program sponsors are SMUD, EY, Greenberg, and Weintraub Tobin. We're grateful for everything they do because they allow us to continue to offer the services that we do. Now, how many of you have heard about CleanStart before? Excellent. Well, we accelerate clean tech companies in the Sacramento region. We provide them with networking, education, and connections to potential fundraising opportunities. Now, in the next few months, we have a couple things coming up. We have our regular Clean Tech Meetup, March 23rd at Valley Vision. That's in the Oak Park area. 28th. I'm reading off this one. March 28th there at Valley Vision. We also have, I want everyone to know this, Cal Seed grants start tomorrow. Cal Seed grants are $160,000 seed funding grants that are great for getting your idea off the ground. They're probably some of the easiest grants you could ever apply for. We have someone actually from the grant farm here, which was instrumental in bringing them to helping the CEC provide these programs through CalCEF to the state. But it's a quick period. You have 10 days to apply for it. We also have Green Drinks, which is monthly, just sustainability meetup. And we're going to be doing the Startup Weekend Sustainability Edition, June 21st. It's a weekend hackathon. And if you want to know more about things, make sure to sign up for our newsletter over there. All right. So welcome to Discover, Discussion, and Drinks. I believe the name was rebranded in the past couple of days because I've heard it discussed differently here. So we're going to have our presenters, and we're going to start with Steve Tourigny. Come on up.
Hey, Steve.
I'm going to give you a little bit of
a boost.
And put this somewhere that won't fall. There you go.
How's that? Is that you're just capturing it for the video? So yeah, I was contacted. I know this guy. I know a bunch of people in here. I was contacted by Laura a few weeks ago to talk a little bit about getting a job in the clean tech sector, and she felt I was qualified for that. And actually, I've had quite a bit of experience, both in finding jobs for myself as well as employing people. I moved here, just to give you a little background, I'm a mechanical engineer, material science background, out of Massachusetts. I went to WPI a long time ago. I just went to my 40th college reunion. And over the years, I've worked for 5 or 6 different companies and have been heavily involved with staffing, as well as I mentioned, finding my own position. So I don't know, this is not as many of the young first year audience that I expected, but I can still talk about it a little bit. Part of this is just part of the issue of getting a job in clean tech is the same as getting a job anywhere else. This is common sense. But I'll touch base on a couple of things. For me, if I put myself in the shoes of someone trying to find a job in clean tech today, the first question I would ask is why clean tech? And I think there's 3 reasons why. I mean, the simplest one is, well, I need a job, and that looks like there's opportunities out here, and that's fine. The second one is more rare, and that is you've had a passion. Maybe it goes back to when you were fairly young. Maybe it goes back to before you went to college, but certainly through college, you've developed this passion in the field. And I think that's a phenomenal reason to want to get into the field. And that's where I can help people probably the most, particularly if they don't have an idea how to get in. And the third one is the path that I followed, which is who's investing? Because it's only where the investment is being made where an engineer is going to be allowed to do the work that they love to do. And so over the years, my career has taken me straight out of school into advanced ceramic material development for a company called Norton Company, which is now a French company, Saint-Gobain. And I was there for about 8 years. And then I actually did a short stint as a technical recruiter, which I guess qualifies me for this talk tonight. I did about 11 months as a technical recruiter. And then 18 years in the semiconductor equipment business, which took me to California. 1990. I moved my family here in 91 for what I thought was a 3 to 5 year startup of a new plant, and then move on to something else. And poof, 28 years have gone by, and here I am in California still, and I probably will never move back to cold places because I can't handle it anymore. But unlike the rest of my family, I pretty much still sound like I arrived here from Boston yesterday. I can't explain that. Maybe a language expert could do that, but I've retained about 80% of my accent, which is kind of fun. And then through the growth of semiconductor, I was working with a company called Ibara and built 3 or 4 factories for them. Spent a lot of time in Japan. It was a real fun job, except for the last 3 years when the industry was collapsing, and I felt like all we did every 6 months was lay off another 10% of the workforce and try to keep it going. And that's not what a growth engineer, an engineer who builds things, really does. But the priority was on my family at that point, having a couple kids, a couple girls at St. Francis High School. And so anyway, make a long story short, that led me into a couple of startups. I worked for a fuel cell company, PEM fuel cell company in Folsom, that I had advised and had been involved with for about a year before I left the semiconductor industry. And then that led me directly into one of the companies I helped found, which was CleanWorld, which is a clean tech company. We manufactured anaerobic digesters for the destruction of organic waste and the creation of fuels and energy. So been quite a wide spectrum there. But the path I followed was definitely one of investment, was who's investing. So if I was and I'm still that way today. I'm a consulting engineer now and working with a number of companies in both technologies and operations and running plants and making plants more efficient. And I'm drawn to basically the growth of companies, the companies that are actually building something and wanting to take off. So that's kind of the overview of how I found positions in my first few positions. And then I would turn right back to an individual today and say, okay, which of those paths are you on? Because if you're on the path just to find a job, I would say be careful, keep looking, and don't be surprised if you find your passion somewhere else within 3 to 5 years. I was kind of unusual, I think, for my period. The two individuals that came to started work with me on the same day, both of them spent 35 plus years with that same company. It was a great company. And I left, and I've worked I think I've been with 6 companies now, 2 of which I helped found. And it was just a different interest. It wasn't right or wrong. And I think knowing yourself and knowing that is really important. And the second criteria I would say for anybody looking for a job in a technical field is get a good feel for the differences between a small company and a large company. So for me, I worked for a very large company. I think the site, Norton Company in Massachusetts, probably had about 8,000 employees. It was about 2 miles on the highway of one plant after another. But I chose to work in a division that had about 200 employees and very, very small company feel. And one of my first projects, first big projects after a year in the company, was transferring to Alabama to help them build a new plant. And that's where I had my first experience with the startup. And I didn't even realize it at the time. I just know I really liked what I just did. I've got to find what about this was that I really liked. And I think what I have to come back and say, if you like startups, you like the newness of it, you like the small team, you like the intensity, and you like a problem where you don't really know what the solution is, but you're going to get there somehow, and you're not intimidated by that. And it's not right or wrong. Some people are drawn that way, and some people are drawn other ways. You can find an equally successful career in staying with the big company. One of the individuals retired a couple of years ago as a director of super abrasives, Dean Arvidsson, a really close friend of mine. And the other one was, after the acquisition, became the CEO of Saint-Gobain USA. So a big job, probably had about 30,000 employees, 20,000 employees. So the 3 of us, our boss, who was my first mentor, was a guy who had an eye for picking people and had an eye for developing young engineers. And to this day, 40 years later, I still reference him and how he was able to find people. So with that, I would say you find which of those categories you're interested in. And then I'm going to wrap up in about 2 minutes here and see if there's any questions. I think that's the most exciting part. But I think the most important thing young people can do today is to really do their research on a company. So I've interviewed a lot of people in those companies, and I continue to interview people to help my consulting clients hire engineers and to develop their teams. And it's amazing how many times somebody comes into an interview who looks great on paper and doesn't know anything about the company. In this day of social media, in this day of Google, there's no reason why you don't know, when you go into that interview, you don't know that history of that company, who the offices are, who the founder was, what their mission is, and frankly, why you would want to work for them, where you can add value. There's no excuse for that today. Having a nice resume is easy. For me, the resume has become nothing but a PDF of my LinkedIn profile. It's a little bit long, so if I want it to be short, we stop with the LinkedIn profile and cut it back. And I think that works out just fine. And that's a nice document, but I would say the research that you do and the preparation you do before you meet with that company is going to be the most important thing. And what's the goal? What's the goal of that interview if you get it? The goal of the interview is to get called back. They're not going to make you a job offer. That's going to happen after a couple meetings. If they do make you a job offer in the first one, fantastic, but it's pretty rare. So I always think about what the goal of the meeting is. You go in there, the goal of the phone call interview is to get the face-to-face. The goal of the face-to-face is to get another face-to-face and keep that going. So that's been my experience, and I've probably hired, since I came to Sacramento, probably 300 or 400 people directly, and all of them technically related, probably 20% of them degreed engineers, 20% of them technologists, and the rest, the balance of the 60% people who had no real technical ability, but they had something that you could read about them, that they had this interest and this drive in learning about the company, and they became the employees and the operators and the technicians in the factory. So with that, I'll just throw it open to a couple of questions because I don't.
So next I'd like to introduce Professor Dixon. He's the chair of the chemistry department, and one of the people that Dean Lorenzo Smith invited from the College of Natural Sciences and Mathematics. Give us 1 second for.
Anyways, like Thomas said, I'm Roy Dixon, department chair for chemistry. I'm an analytical chemist, so you can see the title reflects that. What I did was analysis of alternative fuels in the diesel area. And for this talk, I tried to put a little more into the background and things that might be of more interest to the engineers. Why alternative fuels? Well, it's sort of strange sometimes when you talk about fuels and the product, regardless of what type it is, if it's a carbon-based fuel, it's going to be carbon dioxide. So how's it going to change the carbon footprint? Well, you still get the same emission, but you're replacing carbon that was fossil carbon with something, if it comes from rice straw, for example, that had been in the atmosphere within a few years previously. And so that reduces the buildup of CO2 gases. It can also use waste resources. Look at biodiesel, for example. You go back a long time, people had to pay to get rid of that waste. And then after biodiesel became more important, people were getting paid for a waste product. Another thing is fuel can lead to better quality. That means better performance. Probably the more significant part would be reduction of air pollutants. And then I looked at 2 fuels. The first project I got paid to do that was synthetic diesel. It actually worked out pretty well, I think. And then on campus, I've partnered with mechanical engineering and Rustin Bog at the Stork Center, and they're making biodiesel. And we were looking at checking the quality so that it could be used in lawnmowers on campus. So a little bit on the synthetic diesel. What is it and how is it made? It's produced by a process called the Fischer-Tropsch process. And I'm going to start with the middle of the process and go forward. So you can take what's called syngas, which is carbon monoxide and hydrogen, and then you pass it in front of catalyst. And that's also why I really like this project, because all the catalyst stuff, that's all proprietary. That's Grey Rock Energy's baby. But what they want is good quality fuel. And so if I'm analyzing the fuel, I can talk about that at a place like this. If I was talking about the catalyst, I'd be in trouble. So anyways, so we take, this is what they do, is they take carbon monoxide and hydrogen, pass it in front of catalyst. And so you end up producing basically CH2 radicals, and then those stick together, and you get your fuel here. And of course, it's not really balanced until we add water. And that's the fuel that we're looking at. And actually, it's a very good fuel. If you're just putting carbons together, you're getting mostly linear alkanes, which is great for diesel. Okay, you don't really want branch compounds. The thing that's hard is you're producing these molecules, and they're getting bigger. How do you get them to be the right size? Anyways, that's their problem. My problem is just analyzing the fuel. So how do you get to the syngas? Well, the project I worked on, they actually used biomass waste. And that part really didn't work too well. And I think the company I work with, their aim is looking at the part I showed before. So, but we can take biomass, which we're just showing here as sugar, add heat, and you get CO and hydrogen. Of course, there are a lot more things to this. And they had a lot of problems, I think, with things like corn cobs getting stuck somewhere. So they've kind of moved away from that model, and now they're looking at stranded gas. So that's natural gas that's uneconomical to recover because it's not near any pipeline facilities. And then I was talking to the student who's working on this, and he's all pro-environmental. He's all disappointed, as he's saying, well, they're getting that from fracking, you know. But actually, what's going to happen to the methane otherwise? They're just going to flare it, and when they burn it, it's not that efficient, so there's a lot of methane left. Methane's an extremely strong greenhouse gas, so if we can take that and use it for fuel, it's a lot better. So that's their business model now. So fuel quality, alkanes, pretty much you want around 10 to 16 desired. At least that's what I've been told. And if it's too small, it's too volatile, you can get ignition too early in a diesel cycle. If it's too large, you're going to have solids. So the first samples that we had at room temperature, they had particles in them. And then later on, we'd pull them out of the refrigerator, and there might be a little bit of white material at the bottom. So it was improved. What other products do you get? Branched alkanes. In gasoline, you want branched alkane. Those are good for octane, but you don't want them in diesel engines. Okay. Also alkenes, so there are two problems. I mean, these are more energetic. It's not as good. And then also decomposition's faster, so they won't last as long. Okay, we'll switch to biodiesel. So biodiesel, it's produced by cooking oils, by transesterification. A lot more people know about stuff like this. So here's fat or oil, triglyceride. It reacts with methanol. This is just in an anion form. And then that's our fuel. Okay. Fuel quality. Well, what fatty acid methyl ester, which is, these things. These are the fatty acid methyl esters, or FAMEs. What type of fatty acid is in it makes a big difference. Probably oleic acid from olive oil would be one of the best things. If you have saturated long-chain fats, then you have to worry about those turning into solids at cold temperature. And then if you have a lot of double bonds, you end up getting more NOx, so it's not really a clean fuel. Besides that, we've got other stuff like leftover reactant, glycerol is a product, which we don't really want. These are not very volatile. They're not good to have in fuel. And then typically we use water to wash things off, so we can have water left, leftover methanol, and then with water, you can also get hydrolysis, so you get acids, you get corrosion from that. All right, so what we did is compositional analysis, and then we looked at fuel quality. And for the synthetic diesel, all we did was gas chromatography. And we can use it for qualitative analysis to figure out what the compounds are if we have a mass spectrometer on it, or with the flame ionization, we just determine the amount. So that was all we did for synthetic diesel. It was a lot of fun to work on, too. Biodiesel, we did some analysis by GC also. The only problem there was we had to use a different column, and then we're using the instruments for classes, so we'd have to constantly switch columns, so we didn't really do a lot of work. And then we also worked on a HPLC method, but I'm not going to talk about that. So for biodiesel also, we wanted to make sure fuel quality was good enough that it could be used for a practical purpose. And so, you probably heard the term service learning. This is more service research. So we'd get something done, and then it would be useful. And so typically, you can go to an ASTM method, and there are 15 tests. Okay, a lot of these you require specialized equipment that we didn't have. So we ran some using specific tests. Some we figured out an alternative method. So I'll talk a little bit about that. We didn't really get as far on the biodiesel. So we've worked on some things. Another thing we thought was, well, could we come up with a better screening method? And so two thoughts are, well, we can use IR spectroscopy. I don't know if you remember, but in the slide where I showed all the problematic compounds, almost all of them have OH groups. So that's a good way to check. If your OH group's content is small, your fuel should be good. And then the original fats are non-volatile, but there's no OH group. So we also had another method to look at non-volatile residue. Okay. Actually, I worked on the first charged aerosol detector. It's an instrument that's used for liquid chromatography. All right, so what does this stuff look like? So this is a synthetic diesel, the first sample, and 100 plus peaks. It looks like a big mess. If you compare this to a petroleum diesel, this looks super clean though. So anyways, and it's easy to figure stuff out because you can see repeating patterns, right? Each big peak there is an alkane. So if we take this area and blow it up, we've got these series of peaks. And it's the same whether we're looking at this one or this one, with a few exceptions. Okay, so the biggest peak is the linear alkane. That's the main compound they want. You could look up alkenes. So those have a single double bond in them. And just run standards to figure out what the two things are. The early sample had a lot of branched alkanes and alkenes. We can't really figure out exactly what it is, but we know those are mostly those. And then you can find other things too, like there's a small amount of an aromatic. Okay. And then, so from that, you can take, this is a better sample, and we get a mass composition. So, sorry, this doesn't really look so good, but that's percent from 0 to 8%. You can see it's mostly linear alkanes. What we really want is all linear alkanes in about this region. So we've got too much stuff here. The alkenes are a little high, and also too much of the big compounds. We saw a clear improvement of the samples. I think we were giving them feedback, so they were making better fuel as they went. And one big benefit is petroleum diesel has about 20% aromatics. Other than the benzene, the aromatics were really low in the fuel we looked at. For the biodiesel analysis, actually I don't have chromatograms I could find, so I just showed one of a standard, but it just shows you can pick out the main peak. So if you were to take biodiesel, dilute it, and inject it directly, you can get the analysis pretty easily. We also did residual methanol analysis. This was done by a student. This is just a standard, oops. Shoot. That's the standard. Sorry, I'm pushing the wrong button, I think. Anyways, and then that's the sample. So you can see there's the methanol, just 0.09%. So the fuel sample we got from Stork was really good in terms of methanol. We also did infrared analysis, and these are just standards from 20 to 70 ppm. I didn't show the actual sample, but it wasn't very good. Basically, I think it was up around here or higher. So there are other sources besides methanol that gave poor quality. Basically, conclusions, the synthetic diesel analysis was successful and seemed to improve production as it went on. Biodiesel work, it's actually pretty hard to do because we don't have all the equipment. So we just worked on pieces, and we got progress on different parts, but there's really a lot more to do, especially if we look at the screening methods and try to apply that. I think one thing I'd like to say is that both projects were really successful in terms of student training. One student is now working for a petroleum company. 3 students are working as analytical chemists. 2 are basically doing what most companies would hire a Ph.D. chemist to do. And I want to acknowledge all the people. So Dennis Schutzel, he's part of Grey Rock Energy, and he provided the synthetic diesel samples. And they're located in Sacramento. And then the biodiesel came from Stork, which was originally through Mike Christensen and then Rustin Vaught. And then I had a past student, Alan Morrison. He's the head of the petroleum lab for California Department of Food and Agriculture. And Dennis Schutzel, his company provided a lot of funding. We had other support of student research. And then these are the, oops, sorry. Shoot. Well, I'm probably out of time anyways.
Talking. So piezoelectric is this little piece of crystal that in NASA they started putting electricity into it, like DC electricity, connected it to the battery, and they realized that it starts vibrating. So after a while, many years, they realized that if they vibrated or they put energy like mechanical energy, force into it, it can produce electrical energy, like it can work as a battery maybe. So that idea, there we go. Thank you so much. It started in NASA, and they have worked on it quite a while. There are a couple of countries that they work on it too, and they have implemented the technology. Israel being one of them, and Japan also one of them. So hopefully United States is the third one. Here is a good picture of traffic in Los Angeles, right? So imagine if we extract this much energy, the force, right? So, and this is what I explained just right now. You put pressure on the piece of piezo, and you light up the light bulb. And that's exactly what we have done, and that's where we have started this project. So, how does it work? Again, the cars pass by wherever we are having the piezoelectrics, right? And then when the car passes, you'll have the forces of energy, forces of electric energy. And that magnitude can go as high as 300 volts, okay? With a single piezo, maybe a couple of volts, but the way it is stacked, and the way the mechanical design is formed, it can go as high as 300 volts. And this is actually great, okay? So, we're in the process of patenting the work, so I didn't bring too many details tonight. How to change those pulses to the energy that can be used, for example, for lighting this room or lighting the campus, right? You need power electronic devices, okay? So power electronic devices come in to condition the power, to change the DC power to AC power, and then you can put algorithms to enhance the amount of energy being transferred and stuff like that. So that's all being done by power conditioner circuits, which is our responsibility in Sac State EEE department. So we started like this. It's daunting looking at it. We started with doing simulation in MATLAB software, Simulink, right? And then we put all the electric circuits required for the conditioning into this simulation. What we replaced in here is the pulse. Instead of having the piezo and the force, we just put the pulse. Pulse, and then comes to the power conditioner, brings AC power, and light up a light bulb. Not in the simulation, but in the simulation I can see that there is AC voltage going on here, right? So the bottom line, I don't have too much to say, and I would like to give the thing to you to ask me questions, and I can answer the questions if you want. The bottom line is these couple of lines, that the most important thing to me tonight is, like, if we implement this in this technology, to me as a woman, it's going to look a lot better than the solar. Having any single house in California having solar, okay? This is going to be a lot better, a lot more efficient, and a lot nicer, okay? Let's put it that way. So with the numbers that we have seen, it can, oh my gosh, oh. So we have seen 30 watt per meter. It produces 30 watt per meter. So
single lane.
Single lane, and it's quite a lot. Mm-hmm. So, and again, I apologize because we're patenting the work. My project manager at UC Merced didn't want me to put a lot of details in my presentations. Otherwise, I would have.
So basically, you're collecting a lot of pulses, storing them in the capacitor is
yes.
releasing it, and you're doing
yes.
conditioning
yes.
of that. So, any idea about cost?
The cost is mostly mechanical and road pavement. And I believe it's sort of equal to solar generation at this point. Yes?
When the car rolls over there, it transfers some of the energy to the piezoelectric. So how much does that compare to just rolling over pavement? In other words, is it increasing the inefficiency of the car?
It does not decrease the efficiency of the car. So like you have this material under the pavement, and then you pass by it, this gets energized. There will be DC charge inside this piezoelectric. So then you condition it, you use the energy.
So there's not much deformation
no.
of the crystal?
No. The way mechanical piece is designed, there will not be any damage to the crystal.
But how does that compare to just pavement? So the energy lost by going over pavement versus going over piezoelectric? Is
Are we making energy balance? Are we?
Yeah, are we making cars less?
Yeah, are we making cars less fuel efficient because we're sucking energy into this piezo?
I think I am the wrong person to answer that question. I'm not mechanical, I'm electrical.
The way that you're saying it's implemented is you still have the concrete roadway.
Yes,
You've just put
it's
something
concrete.
underneath.
Yes,
And
yes.
so if the concrete roadway is not deforming any appreciable way over what it does normally, there's really no increasing rolling resistance on the car.
Mm-hmm.
I mean, that's the hypothesis, I guess.
Yeah.
So this is effectively waste energy that the car, the traffic generates anyway, but you're being able to harvest that.
Yes. It's the energy that exists, but nobody uses it. So
you always have some kind of force going into the highway. And the piezoelectric, when you strain it, you have a strain on it, that's when, so you're using that force that would be going into the road bed anyway.
But is it absorbing energy? That's the issue.
It's the strain on the crystal material that causes the So I got a couple of questions.
make sure they're not hard.
Especially LA, is there a difference if cars rolling over at 10 miles per hour versus 60 miles per hour as far as probably the frequency of the pulses, I would think?
There is a difference.
And what are the, you talk about that, and also what's the reliability, what's going to cause these things to fail? What's the wear out mechanism? For solar panels, it's pretty well known what those wear out mechanisms are. What will it be for these old
Okay.
panels?
That one, again, I don't know. We need to study that, we need to see. The place that I've been focused on was the power conditioner. And that's pretty time consuming too.
So does the frequency of those pulses change with the
It does.
speed of
It does. So the pulses that I showed, those pulses, they can get closer to each other or they can get farther away from each other with the speed.
and power is the integration of it?
Yes, the edge detection.
So on your previous slide, you're showing, I think, 300, or no, 30 watts per liter.
Yes.
If you compare that just approximately with the size of a solar panel, which is 300 watts, can you justify using this instead of solar?
Again, my argument is it's underground, and it's the highway that nobody uses. It's not everybody's rooftop, which the solars are usually damaging them. That's my argument.
So the Energy Commission had a program for installing PV panels as roadway. I don't know, do you know anything about that, or how it's where that turned out?
It's being experimented on, maybe not by
Did you have information?
How do they use this in Israel? Again, same concept, or? Okay.
Yes, same concept, and they have started many years ago, actually. Yeah.
Have you explored other applications besides roadways for input energy?
Well, we're going to start actually with UC Merced campus. We're going to light up the campus with piezos over there.
On roadways?
On roadways.
Have you guys explored other potential scenarios aside from road traffic to generate?
Not on this one, no.
Well, there's a lot of work which has been going on for a long time, maybe 30 years when I was in grad school, on smart structures, smart materials and structures.
Right.
Where you try to actuate and sense structural behavior and try to modify that. Is there any of that work which got leveraged?
Yes, absolutely. So the mechanical design, it all goes back to what you just explained. That mechanical design is really enhanced, because when we started the project, everybody was like, oh, you're going to generate 2 milliamps, and that's not going to work. But that's not the case.
Does the voltage output increase as a function of the weight, the force on top?
Yes,
Okay.
yes.
Is there a maximum that it can handle?
Well, the maximum that we got is 300 volts, but then we need to realize how much we can.
I meant the crystal itself, like the max force.
There's not only one crystal in a stack of piezo. There's multiple of them. And the way they have shaped, they're formed in there, again, enhances the voltage level. Yes?
So from an electrical standpoint, I'm envisioning your power conditioner is similar to an inverter in a solar system.
Yes.
Is the inverter done for a whole field of piezoelectrics? Is it done, module on module? How do you?
It should be modular, I believe. It should be modular, depending on the amount of power that we're going to extract from it.
So if you have multiple piezo stacks in a row and a car is rolling over them, you're going to have a sequence of spikes or waves generated across that. Is it one power conditioning circuit for that?
Yes.
Series?
Yes. And then you have algorithms to detect the edges.
And you're accumulating into the capacity. So the capacitor is sort of smoothing out the variation in the pulses.
Yeah, if you had an AC circuit and you had a bridge or a diode bridge to turn that from
you got a bridge
DC to AC, but if you've got a sequence of pulses rippling across this wave of piezo's, so you have to.
So first of all, we make it DC, those pulses. We make it DC with the full bridge. And then after the full bridge, we dump it to the capacitor or the battery, and then we connect it to the inverter.
So what happens when Gary goes back to Indiana and the whole road and the road bed's frozen? Does it still work?
I think it should work. It's just the vertical force that needs to be applied. I don't think the surface being slippery has too much effect on it. Again, I'm electrical engineer. I don't know.
Has anybody built a system to essentially demonstrate the efficacy of this?
We have built the prototype.
You have built a prototype
Yes,
in the lab?
in the lab.
But in Israel, they've implemented some.
They have implemented it in Japan and Israel.
As you mentioned in Japan, they implemented, they use this with the railways in Japan?
Railways, I don't think so. It's highways, I believe. That's what I heard in the Energy Commission.
So is the afternoon peak traffic pretty close to peak demand too, or?
Yeah, well, yeah.
It's good
peak shaving. Yep. Yes, please.
How does ice expansion and contraction affect this and the quality of the road surface?
I think someone else asked it too.
They were asking about the energy output, but you know, ice expansion and contraction really deteriorates road surface. Does water get into the system?
I don't think so, no.
So these are ceramics, right?
These are ceramics, but they have been cased.
They're cased.
Yeah.
They're still brittle in nature.
Yeah.
So
that case is important.
Wouldn't you go through compression when you go through?
I wish I had my project manager here. Mechanical engineer, I don't know any of those. I apologize. So.
Yeah, the question the student raised about, or the I think person raised about trains versus cars. What is the most efficient production? Like, is it heavier vehicles like trains, or is it more frequent vibrations because you've got cars going one after another? How do you model what's going to generate more energy versus less energy?
I think at this point, maybe heavier the better. What we have seen in the lab, the heavier is going to produce higher jump in electricity. But then it depends on how much energy you want to store and how much energy you want to use, and where you have the land available to put them in.
So heavier, does a faster vehicle generate more?
The faster generates closer pulses, and yeah. But then when they're heavier, the jump would be higher.
Closer pulses give you more energy because you've got pulse.
Yes.
It's the overtime.
Well, it's interesting. He's to find several more projects for you. So.
Okay, great.
So the high-speed train that's going in near Fresno, however short it may be.
Yeah. That's how we'll get our investment
Right.
back.
We'll pay off those $5 billion.
Doesn't have any passengers on it, but boy, are we going to harvest electricity.
But on a locomotive, it's probably a lot more effective, right? Because it's a lot heavier. When you talk about a locomotive, not a passenger train, a locomotive.
Yeah.
That carries goods.
Yeah.
And that's what the U.S. is really good at. And it hauls a lot of goods over rail.
If you only get one train every 20 minutes, you know, that might be a problem.
That pulse is, yeah. It's heavy, but it's just one pulse maybe in 2 hours. It's all.
Yeah, multiple pulses.
Yeah.
LA freeways sound like they're better.
Yeah.
Passing
Except for the times on the freeway and the traffic doesn't
Actually,
move.
right. LA
You're stuck.
freeways that move generate more.
That's why everybody, when they moved here from LA, thought it was so great, because at least the wheels keep turning in our rush hours. They're just stuck in the park.
Okay.
Okay, thank you very
Thank you.
much.